Hello, today we're going to be talking about oxidation state, and that's really just another way of saying the charge that an ion is going to have. So if you remember from when we did atomic symbols, an ion is similar to an atom, except the number of electrons doesn't equal the number of protons, so it will have a charge. All right, so now let's talk about how we can predict what the oxidation state for an element is going to be. All right, so the underlying principle here, and this will be the underlying principle with all of the bonding that we're doing, is that an atom likes to have a full octet. This is known as the octet rule. So if you look back at our Bohr model, which we've been using, that means either that this outer valence shell would be completely full, or if the third level had been our outer shell, it would be completely empty. Okay, so either way, now the outermost shell that has electrons is completely full with 8. Okay, the only exception to this is helium, all right, which we've talked about before, and the reason that is an exception is because it only has that 1s orbital, and so it can only hold 2. So for helium, 2 is full. So now let's talk about how we would get to ions that have charges that are different than neutral. So if we take a look at an example like sodium, all right, if you look at your periodic table, you'll see that sodium has 11 protons and 11 electrons. So if we fill in our Bohr model, that leaves 1 electron out here in the valence shell. So we learned before that means sodium has 1 valence electron. And so the easiest thing for sodium to do, if it wants to have a full outer shell, would be to get rid of that 1 electron. All right, so if that goes away, now sodium has 1 less negative charge than it did before, so it will be a positive charge, all right? And ions that have a positive charge, we call cations, okay? So that's how it's pronounced. It's not cations, what sometimes students say, cations, okay? And that just means that it's an ion that has a positive charge. So if we look at another example, we could look at magnesium. It has 2 valence electrons, right? So it's going to give both of those electrons away and end up with a positive 2 charge. Okay. We can also do this with in the other direction. So nitrogen, for example, it has 5 valence electrons. 5 is a lot of electrons to give away. The protons in the middle are not likely to let go of that many electrons. So once we get above 4 valence electrons, what tends to happen is that the atom will steal electrons from somewhere else. So in this case, nitrogen could steal 3 more, and now it would have a full octet, all right, and the charge would be -3. Okay, so the more valence electrons the anion or the atom has, the fewer it needs to steal, and so the smaller the negative charge will be. All right, just like cations are positive ions, anions are negative ions. So the way I remember that is anion has an extra N in it, which looks like negative, and cation has a T in it, which looks kind of like a plus sign. So those are the ones that are positive. All right, another example would be fluorine. So fluorine has 7 valence electrons. It's almost full, all right? So it just needs to steal 1 more, and now it will have a full octet, all right? And that's energetically stable. So that would have 1 extra electron, has a negative charge. Right. So now, if we go back to the pattern we were looking at when we did valence electrons, we saw that on the periodic table it was 1, 2, 3, 4, 5, 6, 7, and 8, right, with the exception of helium. Okay, we can use that information to develop a similar pattern or to recognize a similar pattern for charge. So for the first 3 columns, we only have 1, 2, or 3 valence electrons, so that those will all give away those extra electrons to be +1, 2, or 3, okay? The column with carbon is a little unusual. They tend to not make ionic compounds because 4 electrons is a lot to transfer. So they tend to just not transfer electrons, and they'll make different kinds of bonds, which we'll talk about later in this unit, okay? But then we get to nitrogen. It had 5, remember? So it will need to steal 3 more in order to get to a full octet. Oxygen and the ones in that column all have 6, and so they will need 2 more to get to 8. The halogens all have 7, so they'll need 1 more to get to 8. And then the noble gases are already full, so they don't need to do anything, and they don't tend to form ions. Okay, so that is a general summary of oxidation state, how you would reason through what charge an ion would likely have, and the pattern for recognizing what that is on the periodic table without having to build a Bohr model for every atom.